Hello and welcome to our channel again. Suraj here with new video of mine. And today I'm going to discuss about the part 2 of the Blackbody radiation, which is the experimental graphs to study the experimental graphs of this Blackbody radiation and to discuss about the Stefan-Boltzmann law and the Wiens displacement law and all that things. So in previous video I've given insight into that what exactly is the Blackbody radiation and what are some of the basic fundamental principles of the Blackbody radiation? What is spectral emissive power and all that things? What is the total emissive power, E, absorptive power, and all that things? So in this video, we are going to discuss about the graphs, and in next video, probably we are going to discuss about the Rayleigh-Jeans law and the derivation of the Rayleigh-Jeans law. That how the Rayleigh-Jeans law at the high frequency is not that much good, and I've also shown the graph of the Rayleigh Jeans and all that things in my previous video, so you can watch that particular video. But for now, we are going to discuss about the experimental graphs to study that what exactly this experimental graphs are saying and some deductions from this particular experimental graph, like Stefan-Boltzmann law and the Wiens displacement law. Okay, so let's start about today's video. So first of all, let's recap that what we have studied in our previous lecture. That first of all, this is the graph of the emissive power, and the here is lambda, which is the wavelength, and then it is in microns. So generally, this particular graph is a very accurate graph. And in my previous graph, if you have watched my previous video, in that particular, the graph was not accurate, it's just an approximation. So this is the clear graph. So I hope you all know that what is the here emissive power. So emissive power is generally the intensity or the radiant energy per unit area per unit time. So this is per unit surface area per unit time. This is what the emissive power is, or you can say that it is the intensity, and here lambda in microns. Okay, so what I had told in the previous video is that here, if you heat a particular object, let's say at 904 Kelvin. Okay, so you heat a particular object at 904 Kelvin. So what happens is that the energy that is emitted by that particular object, or let's say black body, because this graph is for a black body. So the energy emitted by the black body has a wavelength from different range, not only of the particular wavelength. Yes, for some wavelength, the energy emitted is maximum. As you can see that in this particular curve, yes, this point. Okay, so if I draw this like this, then yes, the black body emits almost all of the radiation, as you can see that. Not all, but almost. I'm saying it radiates of the light at different wavelength. But for some wavelength, the energy emitted is maximum. Like here in this case, this is a point, this is the lambda for which there is a very high emissive power at 904 Kelvin temperature. So for different temperature, you can find out what is the maximum. It means what is the lambda for which the energy emitted is maximum. And that can be written in a form of the Wiens displacement law. Yes, now let's discuss about what is the Wiens displacement law. So from this experimental graph, Wiens distributed a very important law that lambda m is inversely proportional to the temperature. Okay, so this is what was Wiens law. The meaning of this is that when you increase the temperature, as you can see this in particular case here, it is at 904 Kelvin and the peak is at some lambda. And if you increase the temperature, let's say 1095 Kelvin, the peak of this particular shift to shorter wavelength. It means increasing the temperature. If you increase the temperature, the lambda maximum decreases. It means your wavelength decreases, and you can see that now it is lambda dash, which is smaller than the previous lambda. You understand what this particular law is trying to say? That if you increase the temperature, the peak of your curve starts shifting to the low wavelength. Low wavelength means high frequency. So this is a graph of the wavelength and the emissive power. You can also, in same manner, in same fashion, you can try to draw a graph of the emissive power and the frequency. And that's the general meaning of the Wiens displacement law, where you have to understand that lambda m here is the wavelength corresponding to the maximum energy. Wavelength corresponding to the maximum energy, or you can say that maximum intensity. As you can see that in this particular case, the peak is here. So at 904 Kelvin temperature, lambda m multiplied by the temperature is equals to the constant. And this is the real form of the Wiens displacement law, where lambda m is the wavelength corresponding to the maximum intensity. Because you can see that, let's say for 1469 Kelvin temperature, this is the peak of this particular temperature. And this, after you join the line, you can tell that, okay, at roughly, let's say 2.2 micron means your wavelength. Here, this particular wavelength corresponds to the maximum emissive power or the maximum intensity, and that is the meaning of the lambda m. Lambda m, roughly you can say that, is the wavelength for which the energy emitted or the intensity is maximum. And if you multiplied it by that corresponding temperature, it's always constant. And it is always constant in all the case. For 904, 1095 to 1, it's constant for all of the temperature, because eventually you increase the temperature, the lambda m, which is the maximum which is the maximum intensity for a given wavelength peak, shift to the lower wavelength. This makes this particular quantity constant. So what's the value of the constant? I don't remember exactly what's the value of the constant. You can find it in the Google. But yes, lambda maximum into temperature is equals to the constant, and that is for all of the temperatures, not for a particular given temperature. So this is all about the Wien's displacement law. So this can be written as Wien's displacement law. There's very one important point that you should remember, that increasing the temperature, the peak of your this particular graph shifts to the lower wavelength. As you can see that at 1646 Kelvin, the peak shifted to more shorter wavelength, more shorter wavelength. And that's generally what's the meaning of the Wien's displacement law. That's a very important law. And there is also one more deduction from this particular Wien's displacement law, which is the fifth power law of Wien. So what is this particular thing? So let's start a deduction of this. So it's the fifth power law. Fifth power law. So what's this particular fifth power law is? E max. Here max is the subscript, okay? 1 minute. Okay. Fifth power law, E max is directly proportional to t to the power 5. Okay. First of all, don't confuse between this E. This E is not the energy. This is not energy. This is the intensity. And the meaning of this is that, for a, let's say, first of all, let's clear this particular thing. Okay. So let's study this. Wien developed this law from his Wien's displacement law using the radiation law. And the E max here, first of all, is not same as energy. So E max is not same as the energy emitted. But the meaning is that, suppose that there is a temperature 904 Kelvin, okay? And you all know that for a particular wavelength, the energy emitted per unit area per unit time, which is the intensity, is maximum. It means for given wavelength lambda, the energy emitted is maximum, or you can say that intensity is maximum. So this law tells that the maximum intensity, remember, only that particular point intensity, not all the area. It's the maximum intensity is directly proportional to the t raised to the power 5. There's a big difference between the Stefans-Boltzmann law and this particular law, and I'm trying to disturb the consequences that here this particular E max is the energy emitted for the maximum lambda. For a lambda where the energy emitted is the maximum or the intensity is maximum, and it's directly proportional to the t raised to the power 5. And this is what the fifth power law of the Wiens. Now let's move to the Stefan-Boltzmann law. Second law. Second law. Let's say Stephen's law. So Stephen's law is similar to the Wien's law, but it's different. How? So let's see. So Stephen's law says that if you find out this particular area, let's say area of this particular curve at a given temperature, let's say 904 Kelvin, you find out the area, which will give you the total intensity at all of the particular wavelength. So total intensity, so let's say it's as E dash is directly proportional to T to the power 4. This is the Stephen's law, and by introducing the Stephen's constant, you can think that it is E dash is equals to the Stephen constant into T to the power 4. This is a very important law, and it's different from this fifth power law. The thing is that the main difference between these laws is that here you can see that E max, E max is the intensity for the higher wavelength. Intensity for the wavelength for which the energy emitted is maximum, which is this. This here, if you have some value, let's say 10, so this particular 10 is directly proportional to T to the power 5. But here, it's E dash is the total area, is the total area of this particular curve, and that is the total intensity with all of the wavelength, not of only particular wavelength. But here, E max is for the particular wavelength for which the energy emitted is maximum or the intensity is maximum. And that's the major difference between the Stephen's law and the fifth power law. In Stephen's law, it's the area of the curve, but in the fifth power law, it's not the area, it's for a particular specific point for E max for which the lambda for where there is a E max or the intensity is high, it's directly proportional to T to the power 5. So in more general form, you can write this as E max into T minus 5 is again equals to a constant. And this is the Stephen's law, which is E dash is directly proportional to T to the power 4. And here E dash is the total intensity. Total intensity is directly proportional to T to the power 4, and this is the Stephen's constant. Again, I don't remember the value of this particular Stephen's constant. So here summarizes you about that how to study the graphs of this particular blackbody radiation, that how the peak of the curve moves to the shorter and shorter wavelength by increasing the temperature, and that can be written in a compact manner by the Wiens displacement law, which says that for a particular wavelength, yes, there is the emissive power maximum, and that for particular wavelength, if you multiply it by the temperature, it will be the constant. And it is it's constant for every temperature. At 1095, you can do this, you will find it of the same value that you do for 904 Kelvin. Because eventually you increase the temperature, lambda decreases. And that's the Wiens displacement law. And from the Wiens displacement law, there is another consequence, which is the fifth power law. So what is there, the fifth power law? So it says that, okay, let's say for 1469, let's say it's point at 2. Okay, so it's this particular fifth law power says that for a wavelength for which the energy emitted is maximum. Yes, for 2, the energy emitted is maximum. And that maximum energy emitted, let's say it's 50, is directly proportional to the T to the power 5. Okay, and the meaning of this Stefan-Boltzmann law is the whole area of this particular 1469. The whole area of this particular 1469. That gives you the total intensity in all of the wavelength. But here, this Emax is the intensity for which it's maximum, for the wavelength for which it's maximum. And that's the meaning of the fifth power law. And here is the consequence that there's a big difference between Stephen's law and the fifth power law. Most of the people get confused that both of the things are same because both is intensity, but here it is the total intensity in Stephen's law. But here in Emax, it's not the total intensity, it's the maximum intensity for a particular wavelength. This is the maximum intensity. multiplied by t to the power, which is directly proportional to the t to the power 5. And that's the fifth power law and the Stevens law. Hope you understand this particular graph. And we are going to find out the more general expression so that we can use a mathematical formulation to study these types of the graphs, and that is given by the Rayleigh-Jeans law for low frequency, not for high frequency. So for high frequency, we are going to use the Planck radiation law. So the next video is going on to be the Rayleigh-Jeans law, and after this, the video is going to be on the Planck radiation law, which is more general law than the Rayleigh-Jeans law. Actually, you know that Wiens also proposed a law of the Blackbody radiation, which agrees quite well at high frequency but not at low frequency. So you can say that the Planck law is the combination of both the Wiens law and the Rayleigh-Jeans law, because Rayleigh-Jeans law fails at high frequency and Wiens law fails at low frequency. Planck tried to make it together in a compact manner to make a single law that can use to make this particular graph, or they use to predict a graph and match with the experimental observations. So this is all about the blackbody radiation and Stephen's law and all that things. Hope you find this particular video useful, and if you have any doubt, you can write in the comment section regarding to any topic of the physics. I will try my best to answer that particular question. So thank you.